So, this is the second part of the lecture on sensor cloud. In the first part, we have understood what is sensor cloud, the advantages of sensor cloud over regular sensor networks, and how sensor cloud can help in real life applications. So, we are now going to look at some of the issues in the building of sensor cloud. So, just as a recap of what we discussed before in the first part, when we talk about sensor cloud, it is about integration of two technologies, one is sensor networks and cloud, trying to take advantage of the inherent capabilities of dissemination of sensor networks. So, sensor networks are very much good in data acquisition and thereafter dissemination of this information, and cloud basically is good in terms of information storage, data storage. So, trying to harness the advantages of both is what we try to do in sensor cloud. So, how is it done? It is done with the help of the virtualization capabilities. So, in sensor cloud we are offering sensors as a service through the technology of virtualization, by which these different sensors are virtualized, and these virtualized instances of the sensors are made available to the different users, of sensor cloud. In sensor cloud architecture, typically there are different types of users. One is the end users themselves, the second is the sensor owners, the third is the sensor cloud service provider. So, like this there could be few other different types of actors or the stakeholders as well, but typically we are talking about these stakeholders. So, what happens is the sensor owner is the one who basically makes these who basically procures and makes these sensors available. They own the sensors, they have purchased the sensors, and they have made these sensors available for for use. Sensor cloud service provider is mostly concerned about the supervision, the management of the sensor services. So, they basically in conjunction with the sensor owners, they deploy the sensor nodes in the region of interest, in the area of interest, like in the city or several cities, they will be deploying these different sensors at different points, and then the sensor data are going to be made available to the different users. So, the sensors, the main advantage of sensor cloud is through a virtualized platform, through the technology of virtualization, the different owners are able to access these different sensor devices for performing their own sensing tasks. So, what we have is basically sensors as a service, or even we can think of as the concept of sensing as a service. So, sensors as a service means that the sensors, to whoever requires the sensors, they would be able to get access to the services in the same way as infrastructure is made available through a virtualized platform in cloud to the end users. The similar kind of analogous thing is done over here. Instead of infrastructure, we have the sensors, and the sensors are made available to the users. So, this is the whole idea of sensor cloud, and in this particular backdrop we have to understand that if we have to develop this kind of infrastructure of sensor cloud, how can we do it? So, let us look at some of these different issues. So, first one is the management issue. In sensor cloud. So, we have different types of concerns. What is the optimal composition of the virtual sensor nodes? So, what it means, I will talk about it shortly. The second one is the data caching. So, what happens is, for certain applications it is not required to always prime the sensors physically at the physical level. The data do not change too much. So, data can be cached and can be made accessible to the end users, to the different users. If the data is not very stale, it can be made available to the end users as per the need. And then is the optimal pricing. So, pricing is very much important because it is a service offering. Sensor cloud service provider is offering these different services. So, service offerings are there. So, how the price is going to be like? So, this is the optimal pricing. So, first we will talk about the optimal composition of virtual sensors. So, this particular, if you are interested to look further into the details of this is a paper along with one of my students. We have, this was published in IEEE International Conference on Communications in 2015. So, optimal composition of sensor, virtual sensors. So, let us consider two different scenarios like this of sensor cloud. In one scenario, let us say we have these different sensors that are deployed, and these sensors finally have to be virtualized, right, virtualized. So, how many virtual instances are we going to create? How many virtual instances are going to be created, and what are these instances? It is not going to be like, one physical sensor to one virtual sensor, it is not like one to one mapping between these physical sensors and the virtual sensors. So, we could have, these are like few virtual sensors that are created, and corresponding to this one we have this physical sensor, we have this virtual instance. We could even be having something like this, or even we could have something like this. So, this kind of mapping is possible, So, anyway, so that keeping apart that particular issue. So, how, which sensors, which physical sensors, or corresponding to which physical sensors which virtual sensors are going to be, or how these virtual sensors are going to be grouped among themselves for a particular application on top. So, let us say how we are going to group them to serve a particular application on top. So, that is one issue, and here we are considering that these sensors are physically located in a particular geographical location. So, all these sensors are in one geographic location. Now, it might so happen that in real scenarios, it might so happen that we have different geographical locations, and in these different geographical locations we have, first of all, different sensors in different geographical locations, and the same thing has to be done over here, this virtualization and the composition of these virtual sensors. So, what is going to happen here? Again, we are going to have few of these. So, this mapping has to be done, and this particular virtual instance might be mapped with two different physical sensors in two different geographical area, or it could even be something like this, or this and something like that. So, two things have to be taken care of. A particular virtual instance corresponds to which physical sensors in a particular geographical location or across different geographical locations, number one, and number two is how do you group these different virtual sensors together in order to serve a particular application, So, this is the whole problem, a very fundamental problem to do with the deployment of sensor cloud. So, optimal composition of virtual sensors. The detailed paper, as I said, is available over here. So, efficient virtualization of the physical sensor nodes is one problem. Then how do you optimally compose these virtual sensors? How do you put them together? How do you group them together? So, for this, again, if all these sensors are located in the same geographic region, you have one kind of scheme, and if it is spanning across multiple regions, you have a different scheme. So, why composition of the virtual sensors? Because the sensors are inherently resource constrained. energy constraint, communication constraint, computation constraint, and so on. Dynamic change in sensor conditions also exist. The sensors, they are changing dynamically, not only their duty cycle, their energy resources, etc., their status, they change dynamically. Not only that, but also the physical conditions around them also change. The sensor conditions consequently will also change. Additionally, it might so happen that some sensors, they are, due to some hardware or software failure, they fail to operate, and that is why they do not, at one instance of time they are operating, but at the very next instance they may not be operating. So, we have all these different types of changes that are possible in these kind of networks. The composition of the virtual sensors are non-traditional. So if we talk about traditionally what is going to happen, let us say we have this infrastructure as a service, software as a service, each of these. So, let us say infrastructure as a service or even like software as a service. So, what they are dealing with is just one kind of virtualization of only one type, whether it is the virtualization of software or virtualization of infrastructure and so on. But over here we have a different scenario. Here we are talking about virtualization of different things, different types has to be virtualized. So, it is bit different over here. So, the formation of virtual sensors, as I was telling you before, if all these different sensors are co-located, not only co-located, but also maybe in the same geographic location, they could be virtualized, and these virtual composition, virtual sensor could be formed out of a subset of the physical sensors in this particular manner. And in this particular scenario, it is considered that for optimal composition, we have at the physical level, we have homogeneous sensor nodes. These sensor nodes, they all have their own different specifications, not different specifications, but the same specification. They all have their own same specification, and you group them together in order to form the virtual sensor node. And in this particular scenario, we have the virtual sensor groups, different locations, geographic locations having different sensors, and as you can see over here, through these different labels, they have not labels, but these different legends. We have these we have these different colored sensors denoting different types of sensors in specification, in types. Types means temperature sensor, humidity sensor, these are different types. So, temperature sensor, pressure sensor, camera sensor, these are different types of sensors. So, in this particular formulation, we have considered that not only that these sensors are geographically distributed, they are geographically separated from each other, but they also they can be composed. They are heterogeneous and they can be composed in this particular fashion. So, you can have a virtual sensor which is comprised of, or it is mapped to the physical sensors in one geographic location, and some other physical sensors in another geographic location, some other physical sensor in a third geographic location, some other physical sensor in a fourth geographic location. So, these all will be taken together. They may not necessarily be one and the same, they may not be of the same type, that is they may not all be of the temperature sensor. They could be temperature sensor along with pressure sensor, temperature sensor in one location, pressure sensor in another location, and so on. They all can be put together and clubbed together, abstracted together as a virtual sensor, So, we have likewise different other virtual sensors formed together, and these virtual sensors at another higher level can be put together and grouped together to form virtual sensor groups. So, for example, VS1 and VS2 can be grouped together to form a virtual sensor group, or VS2 and VS3 could be grouped together to form virtual sensor group. In this particular example, we see that a particular virtual sensor group is formed out of these three VSs, the VS1, VS2 and VS3. So, remember one thing that unlike the previous formulation, here we had considered homogeneous sensors at the physical level, and here we have considered heterogeneous sensors on top of the fact that they could be all they could be geographically dispersed. They may not all be in the same geographic location. Different sensors from different geographic locations can be mapped together to form virtual sensors at the higher level of abstraction, and these different virtual sensors again can be clubbed together to form virtual sensor groups. So, in terms of the performance, when we talk about COV1 and COV2 corresponding to the composition of virtual sensors in the homogeneous and the heterogeneous geographically distributed manners, as we spoke about in the previous two slides. So, we have if we look at the comparison of performance with respect to the energy consumption. So, because this is cumulative energy consumption, what we see over here is COV1, this is the plot for COV1 and this is the plot for COV2. So, as we can see over here that the energy consumption basically steadily increases in each of these, and quite understandably that COV2 basically incurs greater energy consumption compared to COV1. And in terms of the lifetime, this is a comparison of the lifetime for each of these two scenarios. As we can see over here that the red colored one is for COV2 and the green colored labels are for COV1. So, lifetime on the other hand increases, not other hand, but lifetime basically increases if we have the homogeneous sensor scenario, where the sensors are from one geographic location and they all have the same specification. So, we have these two different scenarios of cumulative energy consumption and network lifetime and the comparisons between COV1 and COV2. And as I said before, if you are interested to look further into this, you may refer to this particular paper, the optimal composition of a virtual sensor node for efficient virtualization within sensor cloud. This is a paper that was published by us in the IEEE ICC conference that was in 2015 in London. Then we come to the second problem, which is the dynamic and adaptive data caching mechanism. So, before I go to the details of it, I would like to give you a few examples. Let us say we are talking about environment monitoring with the help of different types of sensors, including temperature sensor. Now, in a particular area, the temperature does not change too frequently. So, it is unnecessary to always collect data from the different sensors at very frequent intervals. It is unnecessary, and similarly it is also unnecessary to make the corresponding virtual sensors available to the end users, to different end users. So, it is sufficient if the temperature values are collected and are cached and are stored and be made available to the different users whenever they need access to that information. It is not required to create a virtual instance and then have that through that virtual instance collect or prime that particular sensor to collect the data, to make that sensor sense and collect the data at consecutive instances of time, at subsequent intervals of time by different users. So, it is required to cache. So, there are likewise different scenarios, different applications where this is required to cache. So, we will look at the different ways to cache. So, basically this caching basically introduces two different types of cache. One is the internal cache, the other one is the external cache. So, this example that I was giving you was about the external cache. We will look at the internal cache shortly. So, this caching mechanism basically ensures efficiency in resource utilization. So, caching basically is flexible with the varied rate of change of the physical environment. So, why caching is required in sensor cloud? Because end users request for the sensed information through a web interface, and the allocation of the physical sensor nodes and virtualization takes place, and the physical sensor nodes continuously sense and transmit the data to the sensor cloud, and that is the reason why it is not always required to prime and probe the sensors to sense and continuously send the sensed data through the web interface to different end users. So, practically in some cases the change in environmental conditions are significantly slow, like in the case of the temperature change or humidity change and so on. So, they are not very fast. So, it is not required to always sense through the physical sensors. So, even if you sense, it will give you nearly the same value. The physical sensors are not going to give you vastly different values. So, they remain physically unaltered. Due to the slow change in the environment, the readings are going to be unaltered. So, in such a situation, it is unnecessary to sense, because this sensing would again unnecessarily consume energy which is undesirable. So, we introduced the concept of internal cache and external cache. So, I am going to talk about these two, but before I proceed further, I would like to give you the reference for it. This particular paper was published by us. If you need more details about this internal and external cache and how this caching mechanism operates, you can go through this particular paper, the reference of which is given over here at the very bottom of this slide, and this was published in the IEEE ANTS conference in 2014. And so let us now go back and try to understand what is the difference between the internal cache and the external cache. So, the internal cache basically handles the requests from the end users, takes decision whether the data should be provided directly to the end user, or is it required to recache the data from the external cache. And what is this external cache? So, it is a separate piece of server or hardware which at every certain interval of time it collects the data and stores inside it. So, initially few data are used to transmit to the internal cache. So, this is the architecture of caching. So, this is the existing architecture and this is the cache enabled architecture. On the left we have this existing architecture. So, where we had these different physical sensors, and this is that sensor cloud, and these apps are getting access to the sensors through the sensor cloud through resource pooling mechanisms. Now, in the cache enabled architecture, we have this internal cache and the external cache. External cache could be conceptualized something like a separate server which is outside the cloud, where the data that are made available to the end users through these apps are also cached at the same time at this in this server in this external cache. And so, it might so happen that periodically at different instances of time, it is not required to probe that physical level sensor again. So, the data, if it is not very much stale, it could be fetched from this particular external cache, and even it could be done even better. It might so happen that these different virtual instances that are in the sensor cloud, here the data might be also available. Maybe one user is already using it, and that data could be made available, because if you have to fetch it outside the cloud, that is going to increase the time for fetching, and so you want to keep something over here as well. So, this is this internal cache, and this is how it differs from the external cache. So, external cache is an external server kind of thing. However, internal cache is resident inside the cloud, inside the sensor cloud, and this is how it differs from the external cache. Here is the comparison of performance between the caching mechanism, using internal and external caching mechanisms, and the conventional mechanism. Like as I showed, conventional means this is that existing conventional mechanism, and caching based mechanism means this particular mechanism. And is here what we see is the performance comparison between the two. So, in terms of let us say the total cost, total energy consumption. So, total energy consumption in the case of the conventional mechanism, that means without using the caching mechanism, is shown over here in this particular pink colored plot, whereas the total energy consumption using caching is shown in this particular purple color plot. So, as you can see over here that the total energy consumption decreases quite significantly if we are using the caching mechanism as shown in this particular figure, and how it compares with this pink colored plot. in terms of the network lifetime. Here is the conventional scenario and here is the scenario of using caching. So, as you can see over here, conventionally the network lifetime is much more reduced, and if we are using caching, the lifetime basically improves a lot. So, it is quite significant in terms of the difference between using caching and without caching mechanism. So, caching basically improves the overall network lifetime. And finally, I would like to talk about another issue of sensor cloud. Again, this is taken from a paper that we have published in the IEEE Transactions on Services Computing in 2017, and here we have digged into the issue of pricing in sensor cloud and how we can come up with an optimal pricing mechanism in a sensor cloud scenario, where that pricing mechanism itself is not only optimal, but dynamic in nature. So, the pricing itself is dynamic. So, how does it happen? So, we will talk about that. So, if we look at the existing cloud where IaaS, SaaS, PaaS models are used, there you are talking about homogeneity of services. So, existing pricing schemes in the cloud, the regular cloud, are talking about homogeneous services, whether it is a SaaS service, the PaaS service or IaaS service, and there is no scheme for pricing for sensors as a service. That means, this particular sensor cloud scenario, sensors as a service, SaaS scenario. So, we have proposed a pricing mechanism that comprises of two components. One is the pricing that is attributed to the hardware, that means the sensor, and the pricing that is attributed to the infrastructure, that means the other infrastructure that are in place, the operating system, the other hardware infrastructure, the switches, the servers and so on. So, pricing attributed to the hardware, which is specifically for hardware like sensors, and the pricing attributed to infrastructure. So, PH and PI. So, the goal of the proposed pricing scheme is to maximize the profit of the sensor cloud service provider, maximize the profit of the sensor owner, and to maximize the satisfaction of the end users. So, if we look at this scenario, we have these different end users. Now, you see that what might so happen if the sensing has started from a particular point. So, to the sink when it travels in sensor networks, this sensor data from the source to the sink, it travels via different intermediate hops, and these hops could be belonging to different sensor owners in this particular manner. So, when you talk about a pricing mechanism, we have to take into consideration the pricing due to the hardware cost belonging to different sensor owners, in addition to the sensor cost of the specific owner from where the sensing has taken place of the sensor, from the sensor. So, this sensor data is made available through the base station to the sensor cloud and is made accessible to the end users. So, end users will not only have to pay for the hardware cost of this sensor, that means the source sensor, but also the hardware cost of these sensors, plus also hardware cost, not hardware cost, but the infrastructure cost of other types of infrastructure that are in place, like the base station, the servers, the switches and so on. So, all these also have to contribute towards the price. So, how do we come up with a pricing mechanism? Negotiation is the scenario where the prices can also be negotiated. So, this may not happen in all different cases, but in some cases it might so happen that the end users would be able to bargain and be able to negotiate the price with the sensor owners or with the sensor cloud service provider. So, there would be some kind of a bargaining mechanism in place. It will be a marketplace kind of scenario, a oligopolistic marketplace scenario where this kind of bargaining can take place. So, the focus is on maximizing the profit that is made by the sensor cloud service provider, optimal pricing to the end users, increasing the satisfaction of the end users by considering different factors, all the above three, by considering different factors such as the pricing that is attributed to the hardware while dealing with the usage of the physical sensor nodes, pricing attributed to the infrastructure by dealing with the prices associated with the infrastructure of the sensor cloud. So, these are some of these different issues and the list of different references. If you are interested to know further about sensor cloud, the different works on sensor cloud, here are few references for you. As you can see over here, in our group in the SWAN lab, we have done a bit of digging into the depth of sensor cloud, sensors as a service, virtualization of sensors, composition of sensors, caching of different sensors, and so on. So, these are the different things that we have done. In one of the papers, I will tell you that this particular paper also talks about a comparison between a side by side comparison, a quantitative comparison between sensor cloud and the traditional sensor networks. So, with this we come to an end of sensor cloud. Sensor cloud is a very important technology at present for enabling sensor networks, for enabling Internet of Things, and Internet of Things basically, if you think little bit deep, can be made efficient. The implementation of Internet of Things can be made efficient if we are talking about sensor cloud, and sensor cloud has some similarities with in concept with the fog computing and cloud computing that also has been covered in the different literature, and this is for you to try to understand that what is the difference between sensor cloud, fog computing and regular cloud computing. This is all to do with efficiency, access to different services. These are with respect to these things, basically they differ a lot, and it is not like if sensor cloud is there, we do not need cloud. It is not like that, and also it is not like that if sensor cloud is there, we do not need fog. So, we need all these three things at different times. They are useful for different scenarios. So, we need all of them together. So, all of these technologies are required to build Internet of Things. Thank you.